plus r times x plus r times x squared. Then it keeps going indefinitely, okay? This has a very finite sum. The finite sum of this series is going to be r over 1 minus x if the absolute value of x is less than 1, okay? Here's a second fact, though. This one's not an infinite series, but it's going to be a finite series. Okay. And that is the summation from k equals t to s of r times x to the k. This one's a finite, so let me just point out that this is infinite, and this one is a finite series. Okay, this is going to be r times x to the t plus r times x to the t plus 1, and it keeps going all the way down to r times x to the s. This finite sum, which could have many, many terms, is going to be r times x to the t minus r times x to the s plus 1 divided by 1 minus x. That's its sum, okay? And you could check what this finite series is using fact 1 if you wanted, okay? So those are just two facts I want you to have in the back of your mind, okay? Now, I want us to now consider an example. Okay. So, sometimes you really need something destroyed. And that is, you're going to launch a missile. So you're going to keep sending missiles until it destroys the target. Okay. Now, there's going to be some assumptions that I need, and I also need a random variable. So I'm going to define x. X is the random variable. This is the number of missiles launched until the target is destroyed. Okay, so I'm going to have a table here, x versus the event in S, and I'm also going to have P of X. Okay. Now there's going to be an assumption here, and we're going to assume the success or failure of each missile is independent. And we're going to assume the probability of a hit or a success that this is 80%, so 0.8. Now, the smallest value that x could have here is 1. You need to at least launch one missile. You need to try to hit the target, and then you'll get success on your first try, and its probability is just 0.8. So you try, you're on your first attempt, you get a success, and that probability of success is 80%. You could have a value of this random being 2, okay? And I want to point out the success of failure. That's going to be its complement as 0.2. So that would be failure, then success. And probability that the first attempt is a failure and the second is a success, well, by independence, this will be probability of failure times probability of success. So 0.2 times 0.8. Okay. And then the probability of the first being a failure and the second being a failure and the third being a success, well, that corresponds to x equals 3. Failure, failure, success. That's equal to the probability of failure times the probability of failure times the probability of success by independence. And that's going to be 0.2 times 0.8. 0.2 squared because there's 2 failures. Okay, so 0.2 squared times 0.8. Okay. This can keep going all the way down to the kth value. This would mean success has to be the last event, and there are k minus 1 failures. That's the event in the sample space. Well, you probably guessed that this is going to be using independence 0.2 to the k minus 1 times 0.8. Let's rewrite that. Okay. So, in summary, the probability of having x equals k trials is going to be 0.2 to the k minus 1 times 0.8. I want to abstract that just a little bit further. 0.2, this is 1 minus the probability of success. 1 minus p to the k minus 1 times 0.8, that's the probability of success. This is the general description of a geometric distribution. And one of the key things you're going to be asked to do is to recognize the geometric distribution. A key thing that happened here was that the random variable x was the number of trials until the first success. That's important to recognize when you read the problem description. Okay? Okay, so that's a giveaway for it being geometric. Here's another giveaway. You might ask yourself, are there a fixed number of trials here? And you realize, no, the geometric distribution can keep going on to infinity. Okay, so it can keep going forever and ever. Okay. So here's a question you could be asked. What are the odds, or I could say probability, it takes more than 3 attempts to hit the target. And you'd answer this by using geometric series. So by the way, we're just being asked to calculate this probability. Probability x is bigger than 3 is going to be the summation from k equals, well, it has to be bigger than 3, so 4 to infinity of p of x equals k. Thankfully, we have a very nice formula for how to calculate that. So this is going to be a summation from k equals 4 to infinity of this 0.2 to the k minus 1 times 0.8. And if I write out what this is going to be, well, when k is 4, I'll have 0.2 cubed times 0.8 plus 0.2 to the 4th times 0.8 plus 0.2 to the 5th times 0.8. And this keeps going on and on and on. Okay? So I need to calculate this sum, which is infinite. Well, I'm going to factor out this 0.2 cubed times 0.8 out of each term. And when we do that, we're going to get this. That first term is 1. The second term is going to be 0.2 plus 0.2 squared plus 0.2 cubed, and so on, infinitely many times. Well, this is exactly the geometric series that I described when we first started. And this is going to be, excuse me, my pen is having some difficulties writing. This is going to be what r is. This is going to be x. Okay. And when we use this is going to be 0.2 cubed times 0.8 divided by 1 minus 0.2. And of course, this is going to cancel with the 0.8, and we're going to get 0.2 cubed. Okay, that's the probability. I can ask you a different question. I could ask you, what is the probability it takes 3 or less attempts to hit the target? And if I was to do that, this is asking probability x is less than or equal to 3, which is finite. I could calculate that very easily. But since I've already calculated the probability x is bigger than 3, well, that's the complementary event. And I could just say this is 1 minus 0.2 cubed. And that would be the answer. If I'm the military, one question I'd like to know is, on average, how many missiles should I expect to launch to hit the target? Well, that's a keyword right there, expect. And the answer is, I want this, the expected value of x, which is mu. And we discussed how to compute this. the expected value is nothing more than x times p of x. The possible values of x are from x equals 1 to infinity. This is an infinite sum, and it's rather difficult to compute. In fact, in general, this is going to be the summation from x equals 1 to infinity of x times 1 minus p to the x minus 1 times p. And if I was to write this down, well, I think the first few terms are going to look like this. So let's write down the first few terms. Everything has a p in it, so I'll factor that out. P times, well, when x is 1, this will be q, okay, plus 2 times q squared. Oh, excuse me, the very first term, very first term is going to be when x is 1, and we're going to have a 1 there, plus q, plus 2q squared, plus 3 times q cubed, and so on. Okay, this is an infinite series, but this part right here, let me just point out, this is not geometric. The geometric series looks like this. This is geometric, and it says 1 plus q squared plus q cubed, and so on forever. That's going to be 1 over 1 minus q. Notice we have this extra 2 here. We have this extra 3. That's what makes it not geometric when we do the average. But what I'm going to do here is I'm going to take the derivative. D by dq. And if I take the derivative, I differentiate the 1, I get a 0, so I'm just not going to write it. Differentiate the q, I get a 1. I differentiate q squared, that's 2 times q to the first power. I differentiate 3q squared. I differentiate q cubed, I get 3q squared. And so on. I differentiate this right-hand side, okay? And notice I can use the quotient rule, or I can use the chain rule. And when I do that, I'm going to get 1 over 1 minus q quantity squared. Okay. And I want to point out, I want to go back just a slide. Okay. If I was to write out this term right here, I'll do it in red. When x is 1, I'm going to get just a p. When x is 2, I'm going to get 2 times p times q. When x is 3, I'm going to get p times, 3 times p times q squared, plus when x is 4, this will be 4 times p times q cubed, and so on. This I can factor out a p. This will be p times 1 plus 2q plus 3q squared plus 4q to the third power, and so on. And that needs to be equal to what we wrote down here. I had my powers slightly off. So to match what I had on the previous slide, this exponent right here should be 1 less. So that should be to the first power. That should be squared. Now notice the derivative that we took right here. This derivative matches exactly what we have on top. So that is, I'm going to use this to determine this sum. Okay, right there. And let's do that. That says that this is going to be equal to p times 1 over 1 minus q squared. Remember 1 minus q, p plus q is 1, because q is 1 minus p. So this is going to be p divided by p squared, and this reduces to 1 over p. So the moral of the story is this. So for a geometric the mean value, which is e of x, that's going to be 1 over p. And in this instance, this is 1 over 0.8. And that's how many missiles the government should expect to launch. Now, there's another way to get this value. So, or remember, here's an alternative solution. The mean value, which is e of x, is going to be this moment generating function at 0. So let's check this. By computing mx of t for geometric. So the first thing that you should do is that mx of t, this is the expected value of e to the t times x, and the expected value of e to the tx is the summation of e to the t times x times p of x. X, the smallest value can be as 1. It could go all the way to infinity. So we're going to do the summation from x equals 1 to infinity of e to the t times x. And remember, p of x, the probability of a geometric, is just going to be q to the x minus 1 times p. I'm going to do this one thing right here. I'm going to multiply this quantity right here by q over q. When we do that, I can do p over q times the summation, and we're going to combine these two terms. This will be the summation from x equals 1 to infinity of e to the t times x times q to the x. And one last thing, writing this from x equals 1, just backing up a second. P over q times the summation from x equals 1 to infinity of q times e to the t raised to the x. After all, they both have x in their exponent. I can simplify them like that. And notice that this is a geometric series. So we'll call that R. Using this geometric series, we're going to have P over Q times the summation. Because this index starts at 1 and not 0, this will sum to be R over 1 minus R. And substituting that R is nothing more than Q times e to the t over 1 minus Q times e to the t. We can now simplify this to be P e to the t divided by 1 minus Q e to the t. Okay. So just to quickly write that again, down again, mx of t is going to be P times e to the t divided by 1 minus Q e to the t. Okay. Now, in order to compute the expected value, all we have to do is take the derivative. Okay? And to differentiate this quantity, we have to use the quotient rule. Okay? Well, good thing we remember that from Calculus 1. And remember, using the quotient rule, it'll be the top, which is P times e to the t, times the derivative of the bottom, which is minus Q times e to the t, minus 1 minus Q e to the t, times the derivative of the top, which is P e to the t, divided by the bottom squared, 1 minus Q e to the t, quantity squared. Now, mx prime of 0 says we just plug in t equals 0. And one thing that I'd note is e to the 0 is 1. So we just ignore all of these e to the t's above. So I'll just cross them out in red, and we'll just forget that they're there. That's what plugging in t equals 0 essentially does. Okay. So this is going to be minus P times Q in the top. And 1 minus Q is P, so minus P squared. The denominator is going to be 1 minus Q, quantity squared. In the top, we can factor out a P, so this will be P times Q minus 1. Or excuse me, P times Q plus P. And remember, there's one mistake that I made here, which is that this is a negative and this is a negative, so that makes that a plus. So P plus Q divided by 1 minus Q is P squared. So we can cancel that and that. And on the top, P plus Q adds up to be 1 because they're complementary. So this will be 1 over P. Okay. And if we compare to what we got before, one over P was the expected value that we got. Okay. So let's just summarize. One more thing is that the variance, sigma squared, for a geometric is going to be q over p squared. Okay. And this will be nothing more than e of x squared minus mu squared. And you can check this. So sigma will be the square root of q over p. And you should check this, of course. Now, I just want to remark the hard part for students is typically being able to recognize the geometric distribution. So that is knowing when to use and I touched on this a little bit earlier. So you have to know what your random variable is. You have to be able to match the situation. So the geometric distribution applies when there's a fixed probability p for each trial. So that would be the probability doesn't change from one missile to the next. You have to know that your random variable matches. So the criteria has to be until the last trial. Each trial has to be independent. And finally, something that doesn't answer the question fully but helps narrow it down is commonly, do you have a finite number of trials or an infinite number of trials? So the geometric distribution requires an infinite number of trials. So you know if you have finite, you should not use the geometric. Okay, well thank you. That's all for the geometric.